Hi, my video project is on Acusto optics. So in this presentation I will just explain some basic idea of Acusto optics and some phenomena and some application. I will not go into that much details. So basically we know that the light will get scattered by materials. So when this light passes through a crystal, it will get scattered or refracted, that we know. And this refraction will depend on the refractive index. And the refractive index of the material will depend on its density. So if a sound wave passes through a crystal, suppose this is a crystal, and a sound wave is passing through it will we know that the sound wave is basically a pressure wave, and if a sound wave passes through it the crystal's density will get rearranged in periodic manner. My drawing is not that much well, but still this will get help to get some idea. So its density will get rearranged. There will be crest and trough in for this density, and we are passing ultrasonic sound through this crystal. Then after this, if we pass light through it, it will act as an optical grating. Then the light will get diffracted as same as in grating. So this phenomena is the acousto-optics basically. That means the sound waves is controlling the optics of the system. That's why it is called acousto-optics. Basically there is two phenomena is there. Basically two cases. One is d greater than lambda. That means d means the light beam, and suppose this is the crystal, this is the light beam, and the wavelength is less than wavelength of the sound is less than the the optical beam. Then it will looks like a grating. Then this will get diffracted. But if the beam size is less than, this is the beam size d, and this is capital lambda. But if the beam size is less than the wavelength, that means if it is this much, it will just get deflected. Because reason for that is now it is not looks like a grating. It will just get deflected. Maybe looks like a lens. But our interest is in this portion. For the case d greater than lambda, this is what happening. The light is sound is passing through the crystal, and light is falling on the crystal, and the case is d greater than lambda. And what's happening in d greater than lambda? We will get the diffraction pattern. So that is the case shown here. Both of these regions are scattered or diffracted lights. It will give the orders, and this is the portion which light does not get scattered and light is not diffracted. So we can by this we can select the portion of the light we like. Next is the d less than lambda. Sorry, this would be uppercase lambda. So the light is just falling on the crystal. We use a lens just to collimate this beam, and it is falling on the crystal. Then it will get just get deflected, but we will get the pattern of that some kind of diffraction pattern, but now it is just get refracted. Yeah, we are getting not the pattern as earlier, we are just getting the refracted ray of some kind of order. So that's the difference between both the cases. Now let's look on the diffraction of light by a single ultrasonic wave. We are passing a wave which follows the equation mu sine 2 pi nt x by lambda. This lambda is the wavelength of ultrasonic wave, and n is the frequency of ultrasonic wave. Mu is the amplitude of refractive index, and this sound wave is passing through this crystal, and that will redistribute the density of crystal. Then the crystal will act like a grating. The same as a grating, you will get the diffraction pattern like this. We will get a sinc function. So that's all about it. And this is the angle alpha k, and this is the distance from the central maximum to a particular order, and this k represents the order, not the wave vector. We will use the wave k as wave vector later, but here this is just k, and this is the distance between this lens and the screen. Now there is two kind of diffraction we will observe. We have this equation now, that is small lambda square divided by mu 0 mu lambda square. This mu is the amplitude of refractive index, and mu 0 is the permittivity, and this lambda square is the not permeability. This lambda square is the wavelength of optical wave, that means electromagnetic wave or light, and capital lambda square is the wavelength of the acoustic wave, and we will get a parameter here, rho. If this rho is much less than 1, that is called a Raman-Nath diffraction, and if rho is much greater than 1, that is called a Bragg diffraction. The difference between both is shown in this figure. So here we can see that from this portion it will get diffracted like this, but here it is like getting reflected, and from all of this portion it will get reflected, and we will get a pattern here as same as Bragg diffraction. So this is called a Bragg diffraction. And now let's look on the Raman-Nath theory. In the Raman-Nath theory, after the diffraction, the amplitude distribution is like this. It is actually a lengthy equation. This C is the amplitude of incident light, and this Jk is the Bessel function, and there will be a long argument in the exponential term. Here we have a parameter zeta, and this is defined as 2 pi mu L by lambda. L is the thickness of the acoustic layer, and lambda is the wavelength of optical wave, means electromagnetic wave. So the amplitude distribution is given by this, but the intensity is just the square of this Bessel function of order k. Now Bragg diffraction. For Bragg diffraction, the condition is given here. K vector prime should be k plus or minus k vector, and the mu k equals mu plus or minus k n. N is the frequency of acoustic wave, ultrasonic wave. So that's all about the condition for Bragg diffraction. Now let's look on some application. Main use of acousto-optic is to use in the signal processing and signal modulation. And another major application is Q switching in laser. Another is to find the wavelength of acoustic wave. This A is the let me take the picture of it. Yeah, here this is A and this is SK. This is alpha K. So in an experiment, if we know all of these things, we will get using this equation we can find the wavelength of acoustic wave. Actually this is capital lambda, this is small lambda. So using that we can find this acoustic wavelength of acoustic wave. And I will briefly explain about Q switching. In a laser, usually in a laser there is a active region and there is a pump. This pump will give energy to this active region, and the atoms or electrons whatever in this active region will get excited, and at a random time one photon will get emitted from this, and that will give rise to the stimulated emission for another state, and from that another photon will get generated, then two photons will be generated, and this process will continues and we will get the laser. And this is kept in a cavity, and this will be reflecting, this will be reflecting. If both are reflecting, this light will reflect here and come back to this active region. Then again it will de-excite the states here, that will give rise to more photons, it will get multiplied and it will reflect from here, and this process continues. Then we will get nothing from that. But if this is around a 90% reflecting, some of the light will get exit from here, and the remaining will get reflected and move back and forth, but around 10% will get transmitted, then we will get the laser. But in Q switching, what is happening is at first step this will be 100% reflecting. There is different techniques for Q switching, but this is one case. There will be a medium here, medium modulator here, that will be 100% reflecting. Then whenever we need to take out the laser pulse, this amplification will be going on inside this, but at which time we need to take out the output, then we will pass an acoustic wave through this crystal, this modulator, then the light will get out of this. This is actually a powerful technique to create the short laser pulses, not ultra short, short laser pulses. To generate the short laser pulses which have really high power, we can use this technique. So that's the major application. Another application is modulation of signal and integration of signals in spatial and time extension. If we do the spatial integration, we will get the output in time, but if we do the reverse thing, like if we do the integration in time, we will get the spatial distribution of this thing. That is something like we will use two crystals, then we will in some way we will pass light through both, and both are acoustically controlled, then it will get combined and we will get the output. That is the basic idea, but in both the spatial and time integration we are using different arrangement for that. I'm not going to the details of that. So that's all about the major application. So that's all about it. Thank you.